guys, I'm going to experiment with trying to record some of this so we can put it up for folks who aren't here. Don't know how well it's going to work, but see if I can move this back a little bit. Maybe this will be better. Give it a shot. All right, guys, so we're starting chapter 7 here. Chapter 7 has to do with trig identities. We're going to be doing a variety of things with them, proving the identities, simplifying trig expressions, solving trig equations, all of which treat trig functions more as algebraic objects and functions as opposed to geometric problem-solving tools. So I want to begin today by talking a little bit about what an identity is, all sorts of equations, and I'll start with some algebraic examples. So for example, if we consider the equation x plus 2 equals 5, and x plus 2 equals x, and x plus 2 equals 1 plus x plus 1. So just looking at these one by one, x plus 2 equals 5, that's an equation that has a single solution, right? We subtract 2 from both sides, we get x equals 3. X plus 2 equals x. You can't take a number, add 2, and end up with the exact same number, right? That's impossible. So this is an equation that has no solutions. There's no value of x that will make that true. And then this final equation, x plus 2 equals 1 plus x plus 1, that's going to be true regardless of the value of x, because really on the right-hand side, we have something that's just x plus 2 sort of in disguise, right? So the solution's all real numbers. Or another way of talking about this third equation is that this is an identity because it would be true regardless of the value of the variables involved. All right, so those are some basic examples from algebra. As we get into trigonometry, we can find equivalent equations here that either have a single solution or several solutions, no solution, or for whom the value of the variables don't matter at all. So for example, if we consider sine theta equals cosine theta, that's an equation that has some solutions. You might know, for example, that pi over 4 or 45 degrees is one such solution. Really anything in the form of pi over 4 plus a multiple of pi should work for that equation. We have other trig equations that have no solution. So for example, if we had sine theta equals 2, we know that sine theta can't equal 2 because the range of the sine function is from -1 to +1, so there's no angle that we can choose that would make sine theta equal 2. And then finally, we have some trig equations that are true regardless of the value of the argument. So for example, tangent theta equals sine theta over cosine theta. That's always true, or it's true for any value of theta that's in the domain of both sides of the equation here. So we'd have to exclude values that make cosine 0, but those are also the same values that would make tangent undefined. So this last category of equation is what we call an identity. It's something that's true regardless of the value of theta. We've actually already proven a whole bunch of trig identities in this class. We haven't always called them trig identities. There are names for many of them. I'm going to keep track of some of them up here on the board that we've already proven. So I already have the following. We know, for example, that sine theta is the reciprocal of cosecant, and equivalently cosecant is the reciprocal, cosecant is the reciprocal of sine, right? And cosine and secant are reciprocals. And tangent and cotangent are reciprocals, right? And these properties are true regardless of what theta is, as long as theta is in the domain of the functions involved. And so these collectively are called the reciprocal identities. The names of these various identities isn't super important, but like on a unit eval or something, we might ask you to explain or justify steps that you take in solving an equation or simplifying a trig expression. So it is good to know some of these functions or these trig identities names. You will sometimes see these called quotient identities as well. It doesn't really matter how you call them. We do have a couple other identities that are similar, and these are definitely quotient identities. So quotient identities include actually the one I just wrote there, tangent theta equals sine cosine. And cotangent is cosine theta over sine theta. All right, and some of the things that these particular identities allow us to do is rewrite other trig functions in terms of sine and cosine, which is nice. We have a lot of familiarity with how sine and cosine behave. We know their graphs, we know their zeros, we know some relationships between sine and cosine based on other identities, including our Pythagorean identities. So next, actually even odd, next. By the way, the proofs of all these identities so far can come directly from their unit circle definition. Right, so we define tangent to be y over x, and y is equivalent to sine theta, and x is equivalent to cosine theta. That's all we need to show that that's an identity. Our even odd identities we proved, maybe without calling them such, just by looking at transformations and trig functions. So for example, sine of negative theta and negative sine theta are equivalent because the former is a horizontal reflection of the sine wave, the latter is a vertical reflection of the sine wave, and we've confirmed that the graphs of those two functions are identical. And that's one way, when we're working with trig identities or potential trig identities, that we can identify that we may indeed have a relationship that's an identity. We could take tangent theta, graph y equals tangent theta, graph y equals sine theta over cosine theta. If the graphs are equivalent, that suggests, although it doesn't prove, that we have an identity at hand. So a couple more even odd identities, cosine of negative theta and cosine of positive theta are always equal. We can prove that in the unit circle. We can prove it based on the graph of the cosine function, which means it's an even function that has symmetry about the y-axis. And then finally, tangent of negative theta is equal to negative tangent theta. It's also odd, like sine is. And we can derive some other ones for the other trig functions if we want. Part of what's built into this process of identifying trig identities is keeping track of the really useful ones and not naming and keeping track of ones that are just really slight modifications of identities that we already have. All right, so the third group of important identities for us to keep in mind as we're doing problems today are the Pythagorean identities. And the first one that we proved was that sine squared theta plus cosine squared theta always equals 1. All right, the proof of that came directly from the unit circle. All right, so in the unit circle, we have some angle theta. Right, the radius of the unit circle is always 1, and the two sides, x and y, are equivalent to sine theta and cosine theta. So just by the Pythagorean theorem, we have cosine squared theta plus sine squared theta equals 1. So that's one of our Pythagorean identities. I believe, it was last class or the class before, we also took these, we divided them. We can divide them by sine squared, we can divide them by cosine squared to make two other versions of this Pythagorean identity. We divide both sides by cosine squared theta. Sine squared turns into tangent squared. So we have tangent squared theta plus cosine squared theta over cosine squared theta, which is 1. And the 1 divided by cosine squared theta is secant squared theta. Okay, so sine squared plus cosine squared equals 1. That's usually pretty easy to recognize. Tangent and secant play nicely together. You'll see that in calculus even more so than in pre-calc. But we have a similar Pythagorean relationship here. Tangent squared theta plus 1 equals secant squared theta. And again, if we divide both sides by sine squared, we have a third one, 1 plus cosecant squared theta equals cotangent squared theta. There are a couple other identities that we've covered already. There's some co-function identities. These are identities involving pi over 2 minus x or minus theta as the argument to a trig function. I'm not going to put those up on the board because they're not going to play into the problems that we do today. But in your book and in a list of fundamental trig identities, you will see them listed as well. As you work on the homeworks in the coming week, it's really nice to have a collection of all the trig identities that we've proven so far right at hand. If you have a physical copy of the textbook, you'll find that on either the inside or the back cover of any pre-calculus book. If you're working digitally, you can find it in your textbook. I find it just as easy to Google trig identities, like image search, or find a PDF, and you'll have all the identities right there, and they're named similarly. All right, so these are identities that we have, and we have 3 key skills that we're going to be working on in this chapter. One is simplifying trig expressions. I'll do an example of that in just a moment. The other is proving or verifying new identities. We'll be doing a lot of that throughout the chapter. And then as we get to the end of the chapter, we'll be solving some trig equations. So when we're talking about simplifying trig expressions, we should acknowledge that the term simplify in mathematics is not always clear-cut. It doesn't totally explain what it is that we want to do or when we have a simpler form. But sometimes we can agree that a certain expression is in a simpler form than another one. And I have an example right here. So if we have cosine theta plus sine theta tangent theta. Right, so here's a trig expression, and I would like to simplify this or write it in a simpler form. Well, it's not really clear how I might go about doing this. So what I'm going to start for us, and I hope I can tilt this camera a little bit so we can see it. There we go. I'll move this over a little bit. I'm going to start some tricks or suggestions when we're working with trig identities. One of the things that will often allow us to simplify an expression, or at least to see some underlying structure, is if we rewrite all of our trig functions in terms of sine and cosine. Sometimes we'll get cancellation, sometimes we'll get combination of like terms. So in our list of tips, and by the way, this list is not in order, it's not here's how we always solve these problems, but oftentimes if we rewrite in terms of sine and cosine, we will discover something nice, or we'll see new structure. So for my example here, 2 of the 3 trig functions in question are already sine and cosine. Tangent I can rewrite as sine over cosine using one of our quotient identities. So cosine plus sine times tangent is cosine theta plus sine theta times sine theta over cosine theta. And I'll totally acknowledge that it doesn't look like things are getting simpler yet, right? They actually look like they're maybe getting more complicated. We started with 3 trig functions, we got 4 trig functions. But there is some new structure here. So for example, I can multiply this fraction out and have cosine theta plus sine squared theta over cosine theta. That looks a little bit better there. Okay, so adding to this list of tips for simplifying or verifying trig identities, in addition to rewriting in terms of sine and cosine, we should look for opportunities to use algebra. These algebraic opportunities, we're not going to be able to enumerate all of them, but I'll give some examples of what I mean by algebraic opportunities. If we can add or subtract fractions, sometimes that will again reveal relationships or structure in our expression or equation that we didn't see before. If we can factor, or perhaps do the opposite of factoring, expand, again, we're rewriting our expression in an equivalent manner that might illustrate something about it that we don't already know. If we combine like terms, again, sometimes we'll see something new. And I'll talk about this a little bit later, but I just want to put it on the list now. Use conjugates. And I'll explain that a little bit later. So in the example that we're working on right now, I see an algebraic opportunity. I see a fraction plus a non-fraction. In order to add those two things together, we need to form a common denominator. So this term cosine theta, if I rewrite that as a fraction with cosine theta as the denominator, I'll be able to add these two terms together. Okay, so to do that, I would take cosine theta and I'd multiply it by the fraction cosine theta over cosine theta. Right? That would have the effect of turning it into a fraction with denominator cosine. I'll leave my other term the same way it was for now. Okay, so when I do that, I have two fractions with denominator cosine. That allows me to add the numerators. The first term in the numerator is cosine times cosine, so cosine squared theta. And my second term is sine squared theta. And I'll totally acknowledge in the previous step, it wasn't really clear that this would work out, that this would be helpful. But now that we see it written out in this way, we should be able to identify that there's one of our fundamental identities there, right? Namely that sine squared plus cosine squared always equals 1 if we're talking about the same angle. So then cosine squared plus sine squared, I can rewrite as 1. Really, I have 1 over cosine theta, which is a lot simpler than what I began with. And even more simple than this, 1 over cosine theta by our reciprocal identities is the same as secant theta. And so through a sequence of steps, I took the original expression, which had 3 trig functions in it. I really played around with it. I didn't know how this was going to turn out, right? Or you won't know how this is going to turn out while you're working on it. You have to try some things, right? This list of tips, these are strategy pieces. They're not guaranteed to get you where you want to go. One of the challenges with both simplifying and verifying trig identities is that it can feel like you're lost at times, or you're not sure if the step that you're taking is the correct step. That's okay, that's natural, that's how it always is with these types of problems. I know some students who tend to be more on the perfectionist end of the spectrum have a really hard time sometimes with these problems because they don't really know how they're going to turn out. You have to allow yourself to be lost a little bit in the middle before discovering along the way, oh wow, there's some nice structure here, I can use an identity, and suddenly at the end, it all comes together. But you have to be willing to try things. These aren't the types of problems where if you just stare at them and think really hard and are brilliant, you're going to just know how they turn out. You actually have to try some things here. Okay, so here's an example of simplifying a trig expression. The first WebAssign assignment has quite a few problems like this from 7.1. They really emphasize the simplifying. And the skills for simplifying are the very same ones that we would use for verifying a trig identity. So I'll leave this up for another minute if you guys are thinking about it. We do have to talk about how do we prove that two things are equal? How do we prove that A equals B? And it seems like that would be a very easy fundamental question, but we actually don't talk about it that much in mathematics. So I'll erase this now. We'll talk a little bit about how we do a proof in general, and then I'll do a few examples of verifying trig identities. So if we want to prove that A equals B, well, there's a few ways we can do that. And I want to start with the way that we cannot do this. We cannot just write A equals B and then do something to the equation and decide that it's valid. So we cannot begin by writing A equals B. Right? So for a variety of reasons. This is, in fact, a classical logical fallacy called begging the question, where we assume in our premise the thing that we are trying to conclude. As an example, if I wanted to prove 1 equals 2, which is clearly false, this would not be a good proof. Writing 1 equals 2, okay, well 1 times 0 equals 2 times 0, which means 0 equals 0, and that's true. It would be wrong to conclude that my original premise was true just because I turned my equation into something that was true. I can't do that in mathematics. All right, so we can't begin with A equals B. So what can we do? Well, 2 ways that we can show that A equals B. One would be to show that A is really B in disguise, right? Or that if we rearrange A somehow, suddenly we realize that it's actually B. So we can show that A is B, quote unquote, in disguise. If we did that, we'd start with A, and we'd have a sequence of expressions that are all equal using valid rules of mathematics. And eventually, we would show that, okay, well, once we got down here, we showed that we were actually at B. The other way that we can do this is just the opposite. We could take the right-hand side of the equation and show that B is actually A in disguise. A third option, we'll use this less frequently, would be to show that A actually equals C and B equals C independently. Right, so if we can show that both A and B are equal to some third expression, then that's enough to show that they also equal each other. And there's one more way, and this isn't going to come up in this chapter, but it's good to know, especially as you move into higher math here. We also have what's called an indirect proof. And what we do in an indirect proof is that we would actually assume the opposite. And we'd show that A not equal to B is somehow impossible. It leads to a contradiction. So for example, if we started by assuming that A is not equal to B, and then we showed that as a result, 1 would have to equal 0, that's impossible. That means our original assumption is false. One of the most famous proofs in mathematics uses this technique, this indirect proof technique, the proof that the square root of 2 is irrational, which is considered one of the most beautiful, elegant, short proofs in math, uses exactly this technique. We're not going to use that to verify new identities, but we will use these first 3 strategies, showing that A is actually B, showing that B is actually A, or showing that both sides of the equation independently are equal to some third expression. All right. So, because my camera does not pick up the whole board, I'll have to remember those strategies, and I'll show them in action here. So when you're given an identity to verify, in the textbook and in WebAssign, they're only going to give you things that are actually identities. They're not going to trick you by saying, hey, prove this thing that's not true. But if we weren't sure whether an equation was necessarily an identity or not, one of the things we could do to check that out is to graph y equals the left-hand side and y equals the right-hand side and see if the graphs are indeed the same. If they're not, it suggests that what we have is not an identity at all. All right, so here's an example of the type of problem you'll be asked to do. They'll ask you to verify that a certain equation is indeed an identity. So here we have cosine theta times secant minus cosine. And the claim is that that will always be equal to sine squared theta. All right, so before we jump into this, maybe we can add a few more tips for working with these identities. So we have rewrite in terms of sine and cosine, look for algebraic opportunities. Now that we've talked about how to prove the two things are equal, it should be clear that we really want to work with one side of the equation at a time. And specifically, we want to work with the more complicated side of the equation, or the proposed identity. And the reason we want to do that seems a little counterintuitive, like we'd want to work with the easier side. The more complicated side will have more opportunities for us. They'll have more trig identities hiding out. There'll be more algebraic opportunities. So for example, in example 2 here, on the left-hand side, we have 3 different trig functions. We could do distribution, we could rewrite in terms of sine and cosine. There's a lot of ways that we could get started on the problem. On the right-hand side, sine squared theta, it's not really clear like what we could do with that. You might be able to come up with something involving a Pythagorean identity, but there are fewer opportunities to use the tools that we have. All right, so along with working with the complicated side of the proposed identity, we did this in the last problem as well. We should always be on the lookout for basic or fundamental trig identities. And for now, what we consider to be basic trig identities are the ones that are on this list. By the end of the week, we'll add some new, or by the end of next week, we'll have added some new identities that we can consider in our toolbox as well. My last tip here is don't quit, try anything. Don't stop. All right, sometimes, as we saw in that first example, there's a period in the problem-solving process where you're not sure how things are going to turn out. And it can be easy to second-guess yourself and stop or start over in the problem. And you just have to be patient and know that sometimes it seems like you're totally lost, and then you see some light through the trees and realize that you're almost at the very end of the problem here. So I'm going to try and take my own advice, follow some of the tips here to verify this identity. Again, I'm not going to start by writing this equation. This is like the problem itself here. Line just to designate that. I'm going to start with one side or the other. I'm going to start with the left-hand side in this case, because it's the more complicated, and I see a couple of opportunities that we can use right off the bat there. So we have cosine theta times the quantity secant theta minus cosine theta. And now every line that we write, we're just going to use valid rules of algebra and trigonometry to see if we can get this manipulated, change its form until we hopefully can have sine squared theta at the very end. So two things that we could do. We could start by distributing cosine theta. That'd be totally valid. If you give this problem to 10 students, we'll probably have 3 or 4 different ways that are all completely valid that get us to where we need to go by different means. I think, since I'm not super excited about secant, I'm going to change secant into 1 over cosine to begin the problem, and then I'll have a problem that really just involves cosines. So using one of our quotient identities, or sorry, our reciprocal identity, we can rewrite this as 1 over cosine theta minus cosine theta. All right, so I think the natural next choice then would be to use distribution. I can see that that's going to do some nice things for this first term. And for the second term, we can combine them into a cosine squared term. So if I distribute cosine theta, I'll get cosine theta over cosine theta, which is just 1, right? That's what I get when I multiply these two together. It's important to note, actually, that is true only if cosine theta is not equal to 0. But we already know that cosine theta can't equal 0 because secant theta is in the original proposed identity here. So that value of theta is already out of the domain of the problem. So cosine theta over cosine theta is 1. Cosine theta times negative cosine theta is negative cosine squared theta. And now, maybe surprisingly, maybe not, we actually have something that's very close to one of our Pythagorean identities. All right, so we have a Pythagorean identity that says sine squared theta plus cosine squared theta equals 1. And with one step, we could rewrite that as follows. If we subtracted cosine squared theta for both sides, we also have sine squared theta equals 1 minus cosine squared theta. Now, indeed, this is a new identity. It's not one that we name or keep track of because it's so close to the original Pythagorean identity, where you can take our identities here and rewrite them or do something on both sides if we need to modify them slightly for our use. And since we have 1 minus cosine squared theta, our Pythagorean identity, then we can rewrite this as just sine squared theta. And we're done. What we did is we took the left-hand side and we showed that it was actually just the right-hand side in disguise. Right? Through each one of these steps, we can justify it with a rule of algebra or a trig identity. First step, rewrite using a reciprocal identity, changing secant theta to 1 over cosine theta. Second step, use distribution. That's just a valid rule of algebra. And then right here, we used a Pythagorean identity to rewrite 1 minus cosine squared theta equals sine squared theta. And this is probably pretty typical in terms of the length and difficulty of the problems that we'll have you doing at the beginning here. Any questions about my process here? Okay, so I have a couple more ones here. Let's look over and pull some from our chapter 7 notes. By the way, most of the problems I'm doing today you can find written out in the chapter 7 notes filled in if you want to see all the details if I go too quickly or if it's hard to read the writing here. So let's do this one. Okay, cotangent involves some negative angles here. So cotangent of negative theta times cosine of negative theta. And then I believe it's plus sine of negative theta. Equals negative cosecant of theta. All right, we want to verify this. All right, so for this proposed identity, I think it's pretty clear the left-hand side is the more complicated of the two, so we'll start with the left-hand side. So I have cotangent negative theta times cosine negative theta plus sine negative theta. And again, I prefer to have sines and cosines. If I can't see anything else to do, that's a good step to take. You don't always have to do this, but if you're kind of stuck, not sure what to do next, that's often a good starting place. Okay, so cotangent is cosine over sine, so cosine of negative theta over sine of negative theta times cosine negative theta plus sine of negative theta. Okay, so I can combine my two cosines here, they multiply together, so I can write that as cosine squared negative theta over sine of negative theta. All right, and just as we did earlier on, I think in the simplifying problem, one of the algebraic opportunities that sometimes pops up is the opportunity to add fractions or to add a fraction to something else. And so since I have a fraction here with denominator sine of negative theta, it'd be nice to introduce that into my second term here so that I can add these things together. So to do that, all I have to do is multiply and divide by sine of negative theta. All right, so I originally had sine of negative theta, I multiply the numerator and the denominator, that gives me sine squared negative theta over sine negative theta. And now I have my common denominator. That allows me to add these fractions together. So my denominator is sine of negative theta, and my numerator now is very nicely cosine squared negative theta plus sine squared negative theta. We don't have to worry that that argument of these functions is negative theta. Really what that Pythagorean identity says is if we have sine squared of an angle and cosine squared of that same angle, that will always equal 1. And so again, one of our Pythagorean identities shows up to help us out. So rewriting cosine squared plus sine squared is 1. We now have 1 over sine negative theta. All right, that's looking good. It's good at time to time to like zoom out and remind ourselves what it is we're trying to get in the very end of the problem. We'd like this to equal negative cosecant theta. And we're really close. We know that 1 over sine theta is cosecant theta. The only problem is the argument here is negative theta. The argument here is theta. So we're going to need one more identity, in this case an even odd identity. We know that sine of negative theta is the same as negative sine theta. So we can rewrite as 1 over negative sine theta. And now we're just one step away. 1 over sine theta is cosecant. And so indeed we have negative cosecant theta. Right, so this verification or proof is a little bit lengthier, but it used the same strategy pieces that we've used in all the problems. I started by rewriting in terms of sine and cosine. I saw that I had a fraction, so I chose to make a common denominator, so I'm able to add to that fraction. Once I've done that, I saw that there was a Pythagorean identity hanging out in the numerator, so I changed cosine squared negative theta plus sine squared negative theta into 1. Finally used an even odd identity and then a reciprocal identity to bring us home to negative cosecant theta. So I have one more like this that I'd like to do. It's a little bit trickier, and that involves a technique that we haven't used yet. So I mentioned in the strategy pieces about using conjugates. Where you might remember this from would be the very beginning of the course, where we were interested in doing things like rationalizing denominators. And so as a warm-up here, if we had 1 over 1 plus the square root of 2, we're trying to rationalize that denominator. We can't multiply by 1 plus root 2 over 1 plus root 2, because when we expand that binomial multiplication, we still end up with square roots in the middle term. And so the secret for rationalizing an expression like this is to take 1 minus root 2. That's called the complex conjugate of our expression here. And what's nice that happens when we do this, when we multiply it out, we get 1 minus root 2 in the numerator. And then using FOIL, our outside and our inside terms actually cancel out. The root 2 and the negative root 2 cancel out. We're just left with 1 minus root 2 squared, so 1 minus 2. All right, so that's a technique we've used in the past, hoping to rationalize the denominator. And one thing we'll see with trig expressions or trig equations is that we sometimes want to employ a similar strategy in order to create an opportunity to use some of these identities here. So here's our last example. We have 2 tangent secant, so 2 tangent x, secant x. Of course, our choice of variable doesn't matter for the argument. Doesn't matter if it's theta, t, x, whatever. And then we have this equal to 1 over 1 minus sine x minus 1 over 1 plus sine x. And I just want to double check this. In one of the sections, I miscopied the problem here. I went through all the work trying to verify it, and it just wouldn't work out. And I realized I messed up one of the signs here. So this is what we want to verify. All right, make sure I'm not going off the screen here. It's a little bit hard to see the red writing there, but hopefully this will work out. I'm going to switch to black to actually do this. Okay, so now to start this problem, I don't think it's necessarily clear that one side is more complicated than the other. They both look fairly complex. If I gave this to you, you might choose differently than I do. I see that I already have this one in terms of sine, so I might leave the left-hand side of this alone and work with, sorry, the right-hand side alone and work with the left one a little bit here. So if I start with 2 tangent x secant x, really the only thing that I can see to do here would be maybe to rewrite both of these expressions in terms of sine and cosine. So tangent x is sine x over cosine x, and secant x is 1 over cosine x. I guess if I complete the multiplication there, I end up with 2 times sine x divided by cosine squared x. Now, I don't really see a path in how I could go from this expression into 2 fractions being subtracted. All right, so this might be one of those moments where I say, you know what, maybe this isn't the best strategy. I'm not going to erase this. I'm not going to cross it out. I'm just going to leave it, because at least I have shown that the left-hand side of the equation equals 2 sine x over cosine squared x. Now it's pretty clear to me that the right-hand side is more complicated than what we have on the left-hand side. So I'm going to start working with the right-hand side independently and see if I can either make it equal to tangent x secant x, or equivalently make it equal to sine x times cosine squared x. All right, so I'll start by copying over what I have here on the left-hand side. So 1 over 1 minus sine x minus 1 over 1 plus sine x. And there are 2 reasons why I'm going to do what I do next. One reason is just to create a common denominator so that we can add these 2 fractions together. The other thing that I'm doing here is I'm choosing to multiply by the conjugate of each one of these terms. So if the function that we're looking at is 1 plus sine x, or the expression of the denominator is 1 plus sine x, I'm going to multiply by 1 minus sine x, and you'll see how that helps here. So for my first fraction, 1 over 1 minus sine x, I'm going to multiply that by 1 plus sine x over 1 plus sine x. My second fraction, 1 over 1 plus sine x, I'm going to multiply by a similar fraction, 1 minus sine x over 1 minus sine x. And I want to talk about both my motivation and my justification for doing this. My motivation is twofold. One, I'm going to create a common denominator that I can add these or subtract these fractions with. The second is that when I multiply this out, 1 minus sine x times 1 plus sine x, that's 1 minus sine squared x. That's a lot like our Pythagorean identity, so we'll be able to use the Pythagorean identity there. My justification why I'm allowed to do that is that each one of these fractions is actually just equal to the number 1. So we're not fundamentally changing our expression, we're just changing the form that our expression is in. Okay, so on my left-hand side then, I'll have in the numerator 1 plus sine x. And in the denominator, right, if we multiply this out, again, just be clear, multiply the entire denominator by the entire denominator. Using FOIL, our first term will be 1. Our outside and our inside term are positive sine x and negative sine x, so those will cancel. Our last term is negative sine squared x. Second fraction, numerator is 1 minus sine x. Denominator is 1 minus sine squared x. Same multiplication happening here, and that's being subtracted. All right, so since I have a common denominator, I can write a single fraction with 1 minus sine squared x as the denominator. We'll just be careful when we complete the subtraction here. We have 1 minus 1, so the 1's will cancel. And then we have a sine x minus negative sine x. Sine x minus negative sine x is 2 sine x. And that's good news, right? Because 2 sine x is exactly what we have in the numerator here. That means we're probably getting close to being done with the problem. Okay, so last step here, you can probably see what we're going to do. We've used this identity before. 1 minus sine squared x is just equal to cosine squared x, and that's just a rearrangement of that same Pythagorean identity, that sine squared x plus cosine squared x equals 1. And so for this problem, if you think back to those strategies that I talked about at the beginning of class, how to prove that A equals B, we can show that A is actually B in disguise, that B is actually A in disguise, or in this case, we've shown that each side of this proposed identity is equivalent to 2 sine x over cosine squared x. Right, so we've shown that both A and B are equal to C in this case, and that's enough to show that we indeed have an identity here. I think that's the last example that I wanted to do. Do you guys have any questions about these problems? So this move here, where I multiply by the conjugate, sometimes it's worth doing that, even if you don't need to like create a common denominator. Just by doing that, it sets up a Pythagorean identity in the denominator. So if you see something like 1 plus cosine or 1 plus secant or 1 plus tangent, consider multiplying by like 1 minus tangent or whatever the conjugate would be for that situation. Sometimes it'll put it in a nice form for you.